Okay, so to finish our first part of the discussion, we're going to continue our lecture and finishing the theory part on introducing convective mass and molar fluxes. And before we get into that, let's first take a look at the differences here, or especially the difference for mass transport is that each individual species will contribute to the overall mass or molar fluxes. So different than looking at energy transport, we need to look at each individual components. Okay, so let's first introduce the concept of what's a average velocity. Okay, so let's start with that. So typically we will say that we would be looking at a mixture of n species. So for a mixture of n species, we can define its local mass average velocity. So the local mass average velocity, denoted as just v as a vector. The definition for the local mass average velocity is basically, just summing up each component, which is weighted by their mass fraction. Okay, so definition for that would be what? Would be the overall density of each component add together times its velocity weighted by its density. So I equals to 1 to n. And you can also write this as well. You can also write this as rho over, so the overall density of the fluid or n components times the sum velocity component of each component, and that ultimately equals to looking at the mass fraction of each component times its velocity, I equal to n. Similarly, we can write a more useful term for us as a chemical engineer. We look at molar units. So we can look at the local molar average velocity. And usually we can give it a slightly different symbol, so let's call it V star. And V star here, similarly, equals to basically using mole fraction instead of mass fraction. So it would be the molar velocity of each component multiplied by its molar fraction and add together. Okay. So if we kind of review the diffusion part, which is the mass transfer or transport by molecular mechanisms, let's take a look at that and see how it relates to what we're looking at here. Okay, so if we look at the molar or molecular mass or molar flux, we have a definition right here. So for mass flux, we have the mass flux. Usually we use a lowercase of one component, alpha, equals to what? Equals to rho alpha times its velocity difference with respect to the average mass velocity. And also it obeys fixed first law, so it's going to be negative rho the diffusion coefficient or diffusivity times the gradient of the weight fraction here, mass fraction. And if you write this in molar units, similarly, so molar flux, we usually use the capital J or uppercase J with a star, equals to the concentration of that times its velocity with respect to the average or local average molar velocity, equals to negative overall concentration times diffusion coefficient and the gradient of mole fraction of A. Just like that. Okay, so you can see that we have a difference between the velocity, instantaneous velocity of a component, the difference of that between the local average mass or molar velocity. We sometimes call this as diffusion velocity. So the difference here and here is sometimes referred as the diffusion velocity. Okay, so with that introduced, let's come into our main topic of the day, which is convective mass and molar fluxes. Okay, so coming back to convective mass and molar fluxes, we have convective mass molar flux. So again, let's draw a like a control area, ds, just as we did for the convective energy transport. So we have this control surface. We have x, y, and z. This would be our control surface ds. Okay, so we want to figure out the volume flow rate across ds. Let's look at the x component first. And which is going to be what? It's going to be Vx ds, right? So basically the velocity times the cross-sectional area would be your volumetric flow rate. Okay? So if you look at the mass rate here, it's simply basically multiplying your volume flow rate by the density, right? So in the x direction, we have rho alpha Vx ds. And we can also write it in the y and z component simply as that. So the y component would be rho alpha Vy ds, and the z component would be rho alpha Vz ds. Okay? And so this is the flow rate, right? The mass flow rate. And to get the flux, basically we just need to do what? We need to multiply by the unit vectors, and we will add all three components together and divide by the control surface area. Okay, so what we're going to do here, we are going to multiply, we are going to multiply by unit vectors, which is delta x, delta y, and delta z. We're going to sum them up and divide by the control surface area. So divide by ds. So that gives us the following. That gives us rho alpha delta x Vx plus rho alpha delta y Vy plus rho alpha delta z Vz, and that all equals to rho alpha times the average local mass average velocity. So this would be our convective mass flux vector. Convective mass flux vector, and it has a unit of kilograms per meter square per second. Again, we always like to use the molar flux, right? So for chemical engineers, we like to use the molar flux vector. So if you look at that, we get C alpha delta x Vx, use a star to represent molar velocity, plus C alpha delta y Vy star plus C alpha delta z Vz star, and it equals to C alpha times V star. Okay, so this would be our convective molar flux vector. And it has a unit of mole per meter square per second. Okay, and again, like we did for the energy transport part, the convective energy transport, if you would like to know convective flux across a unit surface, you basically just need to find a dot product between the flux vector and the normal vector of that surface. Okay, so if we write that down, simply saying that the convective mass or molar flux across a unit surface with normal vector we just need to use the dot product. So that would be basically n dot rho alpha times the average mass velocity, or n dot the concentration times the average molar velocity. Let's say C alpha. Okay, so you can kind of see where we're heading to, as we did for the energy transport, the combined energy flux vector. We are going to establish the combined mass or molar flux vector. Okay, so we're going to come into our last part of the discussion, and that will help us to build up our foundation, to our next topic, which is the shell energy or mass balance. So let's continue our discussion. So finally, let's look at the combined mass or molar flux vector. Okay, so for mass, let's look at mass and molar units. So for mass, we define our combined vector using a lowercase n of a specific component alpha should equal to the transport of mass by the molecular mechanism, which is diffusion. So we use the lowercase j and the convective one. So the convective part would be rho alpha times the average mass velocity. So remember, we have the diffusion part, diffusion, and convection add up to be our combined mass flux vector. Similarly, for the molar units, we use the uppercase capital N alpha equals to the capital J alpha star, representing molar units, and again the convection in molar units. Okay, so you can see something interesting here is that the diffusion flux equals to the overall flux minus the convective flux. So it becomes what? It becomes N alpha minus rho alpha times V, and that equals to N alpha minus the mass fraction of alpha times what? Times the flux of the overall flux, right? And similarly, for the molar units, we can get J alpha star equals to N alpha minus C alpha V star, which equals to N alpha minus the mass fraction of alpha and summing up all the other fluxes. So again, what this means is that the diffusion of flux is actually the overall flux of alpha, which is combined, minus the convective part, which is actually just the mass fraction times the overall flux, okay, of all species. Okay, so let's continue. So if we kind of simplify our system to binary systems, then things can get a little bit simpler. So let's take a look at binary cases. So for binary systems, we have the diffusional flux equals to rho diffusivity times this mass fraction. This is based on Fick's first law, but also equals to N alpha minus what we just written down, the mass fraction alpha times the overall flux of the whole system, to N and B, and that actually equals to N alpha minus omega alpha, or W alpha, plus N alpha plus N beta, because you only have two components now. So you can see that N, I think N A, or alpha. So let's correct this. Let's correct this to NA. So NA, NA. So NA now equals to WA times NA plus NB for binary systems. There's only two components, minus the diffusional flux defined by Fick's first law of diffusion, and that equals to rho WA times the overall velocity minus rho DAB gradient of mass fraction. Okay, so the conclusion here is Na equals to rho A times V minus rho times the diffusivity times the gradient of the mass fraction of A. And so likewise for the molar units, for molar units we have capital J star equals to negative concentrations times diffusivity and a gradient of mole fraction of A equals to the combined molar flux of A minus XA times the summation of all fluxes, which equal to NA minus XA times NA plus NB for binary systems. So we get NA equals to CA V star minus C DAB gradient of the mole fraction here. So this one is extremely important, okay? Because this is the most useful form of the combined mass flux, or molar flux actually, that we would use as a chemical engineer when we're doing shell balance, right? So let's kind of review this a little bit. So starting from the combined mass or molar flux vector, right? So you see that for mass transport, the combined flux is basically, you're going to add diffusion and convection together and becomes your combined mass or molar flux. And why are we writing things that we're doing here? Because we are basically expanding the term for diffusion here using a fixed first law of diffusion, right? So these are fixed first law of diffusion. And then, so we can re-represent the combined mass and molar flux in the units of mass fraction. Okay, and that's going to help us to figure out the concentration distribution of individual species as a function of position when we're doing a shell balance for steady state systems. So this content here with the red box is what we're going to use most often, or the most general form we're going to use when we're dealing with problems related to chemical engineering. So I'll write that down for you. So this is the general form used in chemical engineering. Okay, and in some cases, you know, especially for mass transport in solid substances, more related to material science, usually there's no convection. So basically the overall mass or molar flux is your diffusional flux, just as a note. Okay, so we're going to stop here. We're going to kind of finish our introduction to the theory part for diffusivity, for thermal conductivity, and for the combined energy or combined mass or molar fluxes. And this would serve as our foundation for our further discussion. Thank you.